Okay, welcome back. So this is going to be a lesson for linear algebra about dimension and rank. So you know that in the previous lesson we learned about subspaces of Rn. And in addition to learning what the definition of a subspace is, we also learned about the column space of a matrix and the null space of a matrix and the basis of a subspace. Okay, so if you need to, go back and review those concepts. Subspace, column space, null space, and basis. The idea of a basis is going to be pretty important. And, well, let's see what we can do with that in this section. So let's go ahead and get started. So, dimension and rank. Before I can tell you what those two terms mean, we have some preliminary stuff we need to do first. So, let's say we are given a subspace. And we're going to call it H, and a basis, which we will call B. So remember, what is B? If you have a subspace of Rn, I guess I didn't say subspace of Rn, but you know, it's kind of implied by our discussions so far. The subspace H is a subspace of Rn, and what is a basis? A basis is a set of just a few vectors usually, right? It doesn't have the word span in front of it. It's just a set of a few column vectors. How many? Well, it depends. I say it's a few, but maybe it could be a lot. Maybe it could be 100 of them. But it's some finite number of vectors, okay? Now, we're given a subspace and a basis for it. Any vector x in H can be written as a linear combination of the elements of B. What I mean is, my vector x can be written as constant times b1 plus a constant times b2 plus etc. up to constant times bp for some scalars c1 through cp. Makes sense, right? This is not anything new. This just follows from the definition of basis, the definition of linear combination. You know, this is really what a basis does for us. It gets us every element of the subspace. Every element of the subspace can be described in terms of the basis. Since B is linearly independent, that was part of the definition of a basis. It has to be a linearly independent set. The weights C1 through CP used to represent X in this way are unique. Okay, they are unique. That's something that we haven't said before until now, but I think that it makes sense based on what we know about basis and linear combinations, right? If you wrote X as a weight times B1, a weight times B2, and so on, it seems like there should only be one way to do this, and really it's because B is linearly independent. There's no redundant vectors in the basis. So if I have a vector x in my subspace and I choose to write it in this way, I represent it as a linear combination of the basis elements. and I do it in a unique way. It's unique for that x, right? Each x has a unique set of weights. Each x has a unique set of weights. We call these weights the coordinates of x. Relative to the basis b. All right, so that's our first definition for this section, coordinates. It makes sense that we would give these things a name if the set of weights for a particular x are unique. We give them a name. We say the coordinates. What if you put all of the coordinates together and you want to, instead of listing them out like this, doesn't it seem like in linear algebra, instead of writing a list of things, we often think of things as a vector? So I'm going to take these and turn them into a column vector. We have a slightly new notation for this. That thing that I wrote just there, it's a little bit of a new notation. And it equals the column vector of the weights, or should I say the coordinates of x. And this is called before I tell you what it's called, let's look at what this is. I'm saying an element of a subspace. We write a little b down here. That's the new notation. This is to indicate that we're doing it in terms of a particular basis. Remember how if you have a space or you have a subspace, you could have more than one basis for it. So maybe there's like a basis B1 and a basis B2 or something like that. So we specify what basis is this relative to. Okay? So the element x relative to this basis has these coordinates, which are the weights in the linear combination. So what do you think we should call this thing? Well, we call it the coordinate vector. Simple enough. The coordinate vector of x. Again, relative to b. It seems like if we had a different basis, we might have different coordinates. So that's why we have to specify, in regard to this basis, x has these coordinates. In regard to a different basis, x might have some other coordinates. Let's do an example. Okay, so we got some terminology out of the way. Let's do an example. Let's let v1 be 1, 1. v2 is the vector 1, 2. And b is v1, v2. I'm not writing span in front of that. B is just a set of two elements. That's it. Then B is a basis for H equals the span of V1, V2. Because, well, first of all, we know that H is a subspace of R2, right? I didn't write that out. H is a subspace of R2. I know it is because when we define subspaces, one of the main examples we gave of subspaces were things that are written in this form, a span of some vectors. The span of the basis vectors is definitely a subspace. But how do I know that this is a basis? It's because V1 and V2 are linearly independent. What are the requirements to be a basis? All right. I haven't even gotten to the question yet, but I'm just talking about this. What are the requirements to be a basis? The set has to be linearly independent and it has to span the subspace. Well, from this, I can tell that V1 and V2 definitely span H. So we're okay in that regard. Now we can get to the new part. Given x equals some other vector, -2, 3, I'm going to ask you to try to find the coordinate vector of x relative to b. And we have everything we need to find this. So I'd like you to pause the video and try this and see what you can find. Okay, so let's see what we can do. If you're not sure where to start, you say, this is all new, I don't know what to do here. Think about what we said above. Here, I'm going to point to something. I wrote x as a linear combination of the basis vectors. There's like a C1, a C2, and then, those become the things that go in the coordinate vector. So to solve this, I would say we want a linear combination of the basis vectors and we want it to equal x. That makes sense, right? If we could find C1 and C2, put them in a coordinate vector, we're done, right? We're looking for something like this. So we just need to find C1 and C2 that fit this. We can solve this with row reduction. So many things in linear algebra are just row reduction. Set up an augmented matrix to solve this system. C1 and C2 are the unknowns. Do you think that this has to have a solution? Do you think a problem like this has to have a solution? Well, it depends if x is an element of H or not. If x is an element of H, then yes, there has to be a solution. And in a problem like this, it'll probably be set up that way so that, yes, there will be a solution. All right, let's row reduce. I'm not going to write out every little step, but, we want to get zeros to get this into row echelon form. I did this step to get rid of that 0, and then we've done so much row reduction already that I don't want to spend a lot of time on it. I want to just talk about the new stuff. But I did reduced row echelon form, and I got this. So C1 is -7, and C2 is 5. So we are claiming that the coordinate vector is -7, 5. Okay. C1 and C2 were the unknowns in that system, and we solved for them. Maybe it feels a little bit backwards to you because a lot of times when we solve systems, a lot of times x is the unknown, and we're trying to solve for x. And in this case, x is given, and we were trying to solve for the c's. But it still works out as just row reduction. Can you think of a good way to check this answer? That's a follow-up question for you. Can you think of a good way to check this answer? Besides going through these steps again and of course you could always go through these steps again, make sure you didn't make any arithmetic errors. But there's another way to check this. By the definition of coordinate vector, does -7 work and does 5 work as weights for this linear combination? Does this give us... I'm going to put an equal sign here, but really I'm checking to see... Here, I'll put you know what? Let's put an equal sign with a little question mark under it. Is this equal to -2, 3? Okay, let's see if I can section this off. If this works, then our answer must be correct. And you can just kind of check, -7 plus 5 does equal -2, yes. Negative 7 plus 10 does equal 3. I'm going to put a check mark next to it. We checked our answer, and now we're 100% sure that this is correct. So you see how this answer is unique? We only got one set of weights. There's no other possible answer for x relative to this basis. All right, so this was about one full page of preliminary stuff, and the section of this, the section title or the lesson title is dimension and rank, and we haven't really said what those terms are. So now we can start talking about dimension. Definition. I'll tell you, this is an important concept for linear algebra. The dimension of a non-zero subspace. Whoops, let's move this old page away. Non-zero subspace H denoted dim H is the number of non-zero vectors in any basis for H. We're going to show some examples of this right away, but I'll give you a chance in case you're writing that down. It's just the number of vectors in a basis, which we said is usually just a few. It's a finite number. Maybe I should say, in this class, it will always be a finite number. Okay, so it is possible to study linear algebra beyond this class, and, you know, I'm telling you that dimension in our class will always be a finite number. So it is just a number, right? The number of something. So you might have a subspace and say it has dimension 5 or dimension 3 or dimension 2. It's just a number. So example 1. Seems like it's always going to be a positive integer. R2 is a subspace of, what do you think I'm going to say this is a subspace of? I know I keep asking you to finish my sentences for me. It's a subspace of R2. Okay. A basis, I'm not saying the basis, I'm saying a basis for R2 is this set of vectors here. We've talked about this. We could prove that. It's linearly independent set and it spans R2. Another basis for R2 is this set of two vectors, which is also linearly independent and also spans R2. We could prove that. Notice that they both have two vectors. So, using this new word dimension, we could say the dimension of R2 is 2, because that's always going to be the number of elements in a basis. You could come up with other bases. You could make up, that would actually be good practice maybe. Come up with some other bases for R2. You will find that they always have two vectors. Does that mean any two vectors work? Can I just pick any two vectors? Side note. What if I just try any two vectors? Do you think that works? That's not a basis for R2. So, no, you can't just pick any two. You can't just pick any two. They have to span the space, and they have to be linearly independent. It's not just any two that are going to work. So being a basis is kind of a special property. Example 2, Rn has the standard basis. Remember we talked about that, E1 up to En, where those are the columns of the identity matrix of size n by n. So we just demonstrated a basis with n elements. It means every basis is going to have n elements. So the dimension of Rn is n. This is why I say that a basis usually just has a few vectors in it, because we tend to talk about things in this class like, you know, R3, R4, like how big have we really gone, right? We usually are talking about relatively small cases, but you could imagine that it could get bigger. Let's do another example. For example 1 and example 2, I chose R2 as a subspace of R2, Rn is a subspace of Rn. Let's do something else. How about H equals the span of 0, 3, 1, comma 1, 0, 0 is a subspace of R3, and in this case, the dimension of H is 2. Because those two vectors form a basis. We can tell from the way I wrote this that they span H. And I think we can also tell that they are linearly independent. It's a set of two vectors, neither of them are a multiple of the other one. So we've got a basis with two elements, therefore the dimension of H is 2. I want to address something here. In the definition above, I don't think I need to keep moving the page. I'm just going to say, in the definition above, it says the dimension of a non-zero subspace. What's with the word non-zero? What's with that word? Why does it say a non-zero subspace? So let's talk about that. What about, can you have a zero subspace? Yeah, you could have a zero subspace. You could have H equals just the set containing the zero vector. Make sure that that has set brackets around it. H is a set containing this one element, which happens to be the zero vector. We define the dimension to be 0. This is kind of a separate thing that we are going out of our way to define. It's not a part of the above dimension. It's not a part of the above definition. The above definition is for non-zero subspaces. Okay? This is how we define the dimension of the zero subspace. And in parentheses, I'm going to say, we say this subspace has no basis. Okay? So it's not like, it doesn't have one basis element, because you can't just say like maybe the set containing the zero vector and then you think that maybe the dimension would be 1. But that doesn't work, because we don't want to talk about the span of the zero vector, and it doesn't, how do I say this? It wouldn't really be consistent with other subspaces of dimension 1. Other subspaces of dimension 1 are the span of a non-zero vector, which means that they have infinitely many elements. This is different from that. This doesn't have infinitely many elements. This feels smaller than something of dimension 1. So we actually define it to have a dimension of 0. Okay? So, all right, dimension doesn't seem like that hard of a concept. I mean, the previous lesson where we learned about subspaces, we were coming up with bases, and now we're just saying the number of elements in a basis. Has a name. It's called the dimension. Well, this lesson was called Dimension and Rank. So what is rank? Let's talk about that. There's actually another term. In addition to rank, there's another term. We're going to have a definition for rank and something else. I guess the something else didn't really make it into the lesson title, but that's okay. Let A be any matrix. We define, number 1, the rank of A. Written as rank A is the dimension of col A. So do you remember what col A is? That's the column space of A. We talked about that last time. And it's the span of all of the column vectors. So col A is a subspace that we get for any matrix A. And now we just want to talk about its dimensions sometimes, and it has a special name. It's called the rank. So the rank of a matrix A is a number, because it's the number of elements in a basis. The other one is called the nullity of A. And it's written nullity A is the, you probably know what I'm going to say here, the dimension of null A. Null A was the other important subspace that we got from any matrix. It's the span of it's a set of solutions to AX equals 0. So it forms a subspace. We could find a basis. Last time we did an example where we found a basis for col A and null A. And once you find the basis, you know what the dimension of the basis is. Just count up how many elements there are. Make sure it's a linearly independent set, doesn't have anything redundant in it, and then you know the rank and nullity. I guess I'll write this, I think you can probably tell, but I'm going to write this anyway, that we could just say rank A equals dim col A, and nullity A equals dim null A. Right? Dimension of those things. Let's do an example. I'm going to write a problem, and I'm going to ask you to try it. There's going to be 3 parts to it, so wait till I write the whole thing. First of all, I'm going to give you a matrix. The matrix 2, 3, 4, 2, 3, 5. Part A. Find a basis. For the column space of A. Part B. Find a basis for the null space of A. This problem might take a little longer because there's 3 parts to it. Find the rank and nullity of A. The rank and nullity. So I'd like you to... Oh, and just a reminder, we did a problem like this in the previous lesson. At least for parts A and B, we did problems like parts A and B. So I'd like you to pause the video, take a few minutes, and try this. So there's going to be some row reduction in this, right? It feels like in linear algebra, when you're not sure what to do, row reduction is often the answer. But don't just do row reduction blindly. You want to do row reduction with a purpose. You want to understand, like, what is it doing for us? I know that if I row reduce this, it's going to help me figure out where the pivots are. All right, so I'm adding negative R1 to R2. I'm not doing this to like solve a system necessarily. I'm just row reducing A. It's not even augmented matrix of us. Like, we're not adding a right-hand side or anything. Just row reducing A to figure out where the pivots are. I get 2, 3, 4, 0, 0, 1. So this is a pivot location. This is a pivot location. Theorem 13 in 2.8, the previous video lesson was 2.8, says that the pivot columns of A form a basis for the column space of A. So that's why I did row reduction here. I was thinking if I could find which columns are the pivot columns, you know, you could set up the span of all three of these, but the problem with that is I think that the middle column looks like it's redundant. It doesn't look like this would be a linearly independent set if I wrote all three of them. But by doing a quick row reduction step, I can find which columns are important. And we could say, so a basis for col A is, make sure you write set brackets. The basis is a set containing column vectors. Do not write span in front of it. It's just a set of two things. And the two things that I'm going to write are the pivot columns from A. Not from the reduced form, but from A. I found that column 1 and column 3 are pivot columns, so I'm going to take column 1 and column 3. 2, 2, 4, 5. Now, that's my answer to part A. Do you think that there are also other answers to part A? Yeah, of course. Instead of 2, 2, you could remove 2, 2, and you could have 3, 3. That would also work. What if I remove 2, 2 and replace it with 1, 1? That would also work. That would also work because the span of it, it's linearly independent, and the span of it would get us the same thing. Span of this with a 2, 2 is equal to span of this with a 3, 3. I could even change the 4, 5 to some multiple of 4, 5, and it would still work. Make this 8, 10 if you want. Do you see what I mean? Because once you put span in front of it, all those things I just said are equivalent. Linear combinations of them. All right, so part B, we need to find the basis for the null space. So for null space, we want AX equals 0. So this time, if I set up row reduction, I'm going to add the right-hand side as zeros. So 2, 3, 4, 0, 2, 3, 5, 0. And do row reduction on this. So I did row reduction. I got 2, 3, 4, 0, 0, 0, 1, 0. I guess I did the same step, didn't I? The same row reduction step. And then one more row reduction step this time because I wanted to get it into this form. I guess my leading entries are not all ones, so I can't call it reduced row echelon form. By the way, this is not reduced row echelon form because of that 2, but I could multiply row 1 by 1/2, and then it would be. That's okay. The problem didn't say I had to get reduced row echelon form. I'm doing this to figure out where the free variables are. And I see that similar to what we did in part A, I can tell where the pivots are. I can tell that, you know how when you do this, column 1, column 2, column 3 are kind of representing, they correspond to x1, x2, x3. So this is telling me, the fact that there's no pivot in this column is telling me that x2 is free. Now, that already gives me an idea of how many elements are going to be in a basis. But let's go ahead and try to describe the solution set to this homogeneous equation. Row 1 from my reduced form says 2x1 plus 3x2 equals 0. We like to write basic variables in terms of free variables. So I could say 2x1 equals negative 3x2. So x1 equals negative 3/2 x2. That's row 1. What does row 2 tell us? It's only 2 rows. I guess you could have done these in either order. What does row 2 tell us? It says x3 equals 0. That's okay. x3 can be 0. So I think we could describe the solution set in parametric vector form, because I think that's going to help us. Describing the set in that way is going to help us do what we need here. So x is equal to, let's call it x1, x2, x3. You know that there are 3 elements of x, by the way, right? When you've got a matrix of this size, this is a 2 by 3 matrix. The matrix I was given is 2 by 3. If you're questioning, should x have 2 variables or should x have 3 variables, just remember that there's like an x1 column, an x2 column, and an x3 column. There are 3 variables, 2 equations. We found negative 3/2 x2, x2, 0. So pull out x2, and you could say negative 3/2, 1, 0. This is parametric vector form, this right here. Okay. How does that look? A free variable times a vector. x2 can be anything. x2 can be any real number. All right, so the solution set is the span of this one vector. That's the solution set. This is the solution set for ax equals 0. Any multiple of that vector works. So basis for null A is, what do you want to call this? I guess, should we call it B? We already used B, like a capital B was already used in part A. So if you want to, you could use a different letter here, or you could call it like B1 and B2. That might be nice. Or maybe you could call it like BC and BN or whatever. But it's okay if you just call it B. So the basis is the set containing this one vector, and I'm just calling it B, because we're in a different part of the problem anyway. Let me go ahead and put boxes around my answers. So this is the answer to part B. And I'm going to go back and put a box around my answer from part A. Can we fit these both on the screen at the same time? Almost. Yeah, there we go. All right, answer to part A, answer to part B. We found a basis for the column space, a basis for the null space. Part C is going to ask us for the rank and nullity of A. Can you see what they are? Yeah. Yeah, all of the hard work is done. Part A and part B, that was all of the hard work. Part C says to find the rank and nullity. It's the number of elements in these bases. So from the above work, we can see that the rank of A is 2 and the nullity of A is 1. The number of elements in the basis for the column space and the number of elements in the basis for the null space. One is one element there. I was saying earlier that you could come up with other bases, like this basis right here. What if you say, I don't like fractions? What if you say, I don't like fractions, and I'm going to take this and multiply it by 2? Take this entire vector, multiply it by 2. When you take the span of it, you still get, all multiples of the vector, so it would still work. And you would have -3, 2, 0, and you would call that your basis. It would also be a valid basis. I would suggest that you don't do that kind of stuff because this basis that we found is the basis that we got naturally from solving the problem. So I feel like this is the most natural basis for this space, and that I would like to leave it that way because it almost shows where it came from, But regardless of that, I'm saying technically there could be other ways to write the basis, but the important thing is any basis for this space is going to have a dimension of 1. You're never going to add another column vector to it or anything like that. Okay. So for this problem, we had a 2x3 matrix. We found a rank of 2 and a nullity of 1. Do you think that there's some relation to this? Here, I've got something to show you here. Got something to show you. Well, I can't fit it all on the screen at once, but let's just talk about what we did. In part A, we looked at how many pivot columns there were because there was a theorem that said that pivot columns form a basis. There were 2 pivot columns, and the rank wound up being 2. In part B, it was kind of like the opposite. We were looking at which columns do not have pivots because the number, the columns that do not have pivots are going to represent free variables. The number of free variables is going to influence what the solution set looks like, and it's going to basically be the number of elements in this basis. So because we found 2 pivots, we wound up with a rank of 2. There was 1 more column in the matrix, did not have a pivot, it had a free variable. That wound up being the 1 for the nullity. So it almost seems like if you know one of these, you can find the other. If I told you that there were 2 pivot columns, do you think that you could figure out that this was going to be a 2 and a 1 for a matrix of this size? We have a theorem that says this, and this is called Theorem 14, the rank nullity theorem. And in this class, we have a bunch of theorems. A lot of times we'll have like a theorem 13, theorem 12, but most of the theorems don't have names. When a theorem has a name, that usually means it's important. Okay? So the rank nullity theorem is important, and it's just one sentence, and it says, if a matrix A has n columns, then the rank of A plus the nullity of A equals n. That's it. That's the theorem. So it's not just a coincidence that we got a 2 and a 1. This matrix had 3 columns, so we had to get answers that add up to 3. 2 plus 1 is 3. So yes, it does seem like if we find the rank, if we know the size of the matrix and we know the rank, we can figure out what the nullity is. And vice versa. If we know the size of the matrix and we know the nullity, we can figure out what the rank is to make sure it adds up to n. I guess technically there's a third option, is if we know the rank of a matrix and the nullity of a matrix, it can tell us the size of the matrix. But usually you would know the size of the matrix already. So why is this true? We saw this happen in the one example that we did, and it seems like it has to do with the number of pivot columns. So I'm not going to give you a rigorous proof right now. I think the one example that we did helped make this seem convincing, but I'm just going to give you a rough sketch of the proof. The rank of A equals the number of pivot columns. And that's by theorem 13. The nullity of A equals the number of free variables. I guess, yeah, I should say, when solving AX equals 0, just to be clear, free variables for a matrix A. It's really free variables for this system, AX equals 0. Add these together, and what do you get? The rank plus the nullity equals the number of columns. Because every column is going to either be a pivot column or a free variable. So when you add them all up, you have all columns. That's not a very rigorous proof. That's not even a nice way to write a proof, but that's a rough idea of why. I'm going to say that the full proof is in the textbook. Not in this section, though. Full proof in textbook section 4.6. So it's actually in a different part of the book. But this is the key idea. So this is a rough sketch of the proof. Okay, hi everyone. So we do still have a little bit more of this lesson, but I just thought we would take a quick little break, and we've been going for a while. Thought I would take a break, give us a chance to take a breather, catch your breath. All right, so we just had the rank nullity theorem, and I'll tell you what's coming up next is we're going to do a couple of examples of using it, seeing what it can do for us, and then we're going to revisit the invertible matrix theorem. And that was something that we said in the previous lesson, or maybe it was even earlier. But when we talked about characterizations of invertible matrices, that's when we had the IMT, the invertible matrix theorem. The reason I'm telling you this now is because you remember we had that big handout, that big theorem handout. We're going to revisit that, and I've posted a new handout for this lesson, revisiting the invertible matrix theorem. So if you want, now might be a good time to go and grab a copy of that from the same place where I always post worksheets and handouts and things. All right, and we're going to continue, though. We've got some examples of rank nullity theorem before we get to the IMT. Okay, let's go ahead and get back to it. So we've just said the rank nullity theorem, and it makes sense based on the previous example we did, but I want to show you some more examples. Let's move the whole thing away. I think it's a pretty short theorem. I think we can remember it. All right, this example, I'm going to walk us through this because I think that there have been a couple of problems I've already asked you to do today, so I'm going to do this one for us. Let's consider the matrix A equals 1, 0, 0, 0, 1, 0, 0, 0, 1. That matrix looks familiar, right? That matrix has a name. That is the identity matrix. We sometimes call it I, but it's okay to call it A. Let's talk about the column space. So, I think looking at the identity matrix might be interesting since it's one of these important matrices, fundamental matrices. So, what's the column space? The column space is going to be the span of every column that has a pivot position. Now, remember, what I just wrote has the word span in front of it because I didn't say this is a basis. I said this is the actual column space. The actual column space is the span of these three vectors. Notice that this happens to be R3. These span all of R3. So I expect the column space of A to be a subspace of R3, but in this case, it's actually all of R3, which is, kind of the biggest subspace of R3 that you could get. R3 is a subspace of R3. And let's talk about rank. Rank of A, which is the dimension of col A. Number of elements. This is the dimension of R3 then, because we said that the column space of A is R3, and we've already said the dimension of R3 is 3. We could see it from the three vectors that we could write as a basis, and also because we said earlier that the dimension of Rn is always n. How about the null space? What's the null space for this matrix? I mean, by the rank nullity theorem, I think I know what the nullity is going to be. But let's just go ahead and do this anyway. Ax equals 0. What does the solution set look like? We would take the augmented matrix, with the right-hand side being zeros, and we would try to row reduce. Well, it's already row reduced. It's in reduced row echelon form. We can't reduce any further than this. Are there any columns that seem to suggest that there are free variables? No, no free variables. x1, x2, x3, they all have pivots. So what is the solution to this? Well, you could actually read out what this is saying. Row 1 is saying x1 equals 0. Row 2 says x2 equals 0. Row 3 says x3 equals 0. So this only has the trivial solution. X equals the 0 vector. We know that a homogeneous equation like this always has at least the trivial solution. And in this case, that's the only one. So the null space of A, which is supposed to be the set of all solutions, it's this set. And the nullity of A, which is the dimension of null A, is the dimension of the set containing only the 0 vector, which earlier we said that is defined as 0. Well, I knew that we were going to get a 0 anyway, because we got a 3 to this answer, so I knew this was going to be 0. But now we got to see the mechanics of how that all plays out. Everything seems to make sense. I was expecting a 0, and we did get a 0. So the rank nullity theorem how does that look for this problem, or for this example matrix? Rank A plus nullity A is supposed to equal n, and for this problem, it's a 3 plus 0 equals 3. So everything checks out. So that wasn't so much a problem that I was asking you to solve. It was just, I thought we should demonstrate it on this matrix to show you that it is possible that one of these things could be 0. Oh, I have a question. Do you think it's possible for the rank to be 0? I guess if you have a 3 by 3 matrix like we did, do you think it's possible for the rank to be 0 and the nullity to be 3? And what do you think that matrix would look like? How about this? Let's make it a problem. Let's make a problem out of this. Let's say example. Give an example of a 3 by 3 matrix A with nullity A equals 3. I'd like you to try that. I think that's a cool little question. So why don't you pause the video, take a minute, and see if you can come up with that. And see if you can justify your answer. All right, so I'm going to show you there is an answer to this. We should try to find an answer and also justify our answer. I guess in order to have a nullity of 3, we would want AX equals 0 to have 3 free variables. That's the most free variables that it could have. So I think what we should do is let A be a matrix of all zeros. That guarantees that it's going to have no pivots. I guess the augmented version, like if we were to try to set this up as if we were going to row reduce, but I don't think there's actually going to be any row reduction. But set it up as an augmented matrix for the system, pretending that we were about to row reduce, and then you say, oh, look, there's nothing to row reduce. And this column is telling me that x1 is free. This column is telling me that x2 is free. This column is telling me that x3 is free. And the last column was from the right-hand side, so that's fine. There is no x4. It's a 3 by 3 matrix. So they're all free variables, so this seems to work. I'm going to put a circle around this. I'm going to say that is my answer. But I'm going to show a little bit more. I want to go into more detail. Let's see how this all works out with rank and nullity. I know I only asked you about nullity. So I guess what I just wrote is a satisfying answer to the question. But let's kind of go into more detail. If all of the variables are free, why does that mean that the nullity is 3? So the solution set for AX equals 0. We often like to write things in parametric vector form. So X would be X1, X2, X3. They're all free. You know that in parametric vector form, we usually write a free variable times a vector plus a free variable plus a vector. There's 3 free variables. I think that's the most we've ever seen in a problem. So how do we write this? What goes in here? Well, in order to make this add up to this, x1, x2, x3, you would use 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? That's parametric vector form. So null A is the span of these 3. Because, they showed up in the parametric vector form. They're all linearly independent. Here we go. Hey, you know what? Something interesting happened here. What's the span of these three vectors? This is a subspace of R3. It happens to be all of R3. The biggest subspace that you could possibly get from R3 is R3 itself. So in this case, when you start with this matrix A, the null space is the entire space. So the nullity of A, which equals the dimension of null A, is 3. We did it. We did demonstrate a matrix with nullity 3. Now, by the rank nullity theorem, this means that the rank should be 0. Can we tell that the rank is 0? I think we could tell that the rank is 0 here. Notice that the column space of A is the span of the columns. Now, we can always write the column space of a matrix as the span of its columns. By definition of col A. Let me move this other page. Right, all I did was take the columns of A. So that definitely is the column space, because that's what the definition of column space says. You do span of all of the columns. Now you might look at this and say, that's not a basis though, right? But it's okay, because I didn't claim that this was a basis. I just said this is the column space. That is true. But maybe a more concise way to write this set is, this is the set containing only the 0 vector. Because what is it? It's all multiple, it's all linear combinations of these columns, right? It's all multiples of 0. What are all multiples of 0? 0. So the rank of A is the dimension of this set, which we have defined that dimension to be 0. And just for completeness, we will verify what the rank nullity theorem says. We're supposed to get rank of A plus nullity of A to equal n. N is the number of columns, so we did get 0 plus 3 equals 3. Everything checks out. So I kind of asked you that as a question, and then we kind of went a little bit beyond the question and discussed it further. But you know, I like that the examples that we've done so far of the rank nullity theorem, we've done kind of the two extreme cases, haven't we? I'm just gonna remind you that earlier we did this one. We had 3 plus 0 equals 3. And now we have 0 plus 3 equals 3. I am calling those like the two extreme cases, the two edge cases, where one of the things is 0. But earlier today, we saw an example. I'll show you on the page from earlier. We had an example where the rank of A was 2, the nullity of A was 1, and they did add up to 3, which was the number of columns. It seems like we're doing a lot of 3 by 3 things today, or 2 by 3, or 3 by 2, or just that overall size. So I have another question for you. Give you a moment just to make sure you've got all that. Okay. Here's a question. Given A equals a 3 by 3 matrix, but I'm not going to tell you what the entries are. They're unknowns to us right now. Suppose B1 is a basis for the column space of A. and B2 is a basis for the null space of A. If B1 is a set of only one element, how many elements are in B2? I'm not going to ask you to pause the video. I'm just going to ask you to take a few seconds to write this down and then take a few seconds to think about the answer. I think this problem takes longer to write than it does to answer, right? The answer has to be 2 by the rank nullity theorem. All right, so I wrote this out just to give you a question that had a matrix where we don't know the entries, but really this is a simple problem if you think about it. The number of elements in the basis for the column space, that's known as the rank. The number of elements in the basis for the null space, that's known as the nullity. The rank and nullity have to add up to 3 because there are 3 columns. So if you are told that the rank is 1, then the nullity has to be 2. The key idea is that if we know the rank or nullity, we automatically get the other one for free, provided that we know how many columns there are, which we usually do. So we've done some good examples today of things involving dimension, rank, nullity. We can see how it can help inform us about subspaces and matrices. But now what we'd like to do is get back to kind of the big picture of the course. And one of the big picture ideas of this course is we would like to revisit the invertible matrix theorem. Which we might sometimes call the IMT. Okay? We talked about this back in the textbook section is 2.3, I believe, characterizations of invertible matrices. And we had a big theorem. So I have a handout and it's posted in that usual place where I post worksheets and handouts for you. So I'd like you to have that. I guess we could look at it a little bit on the projector, but probably easier to read if you just have a copy of it yourself. Here's what we'll do. We'll move the old page out of here. We'll move this up. We'll try to look at some of this. This is the handout for this lesson. So, like I said, we looked at this theorem originally, the invertible matrix theorem, in section 2.3, but now we are adding to it from section 2.9. So let's try to look at, let's zoom in a little. Let's remind ourselves, don't just look at the new stuff, remind ourselves of how the theorem starts out. It says, let A be a square n by n matrix. So it has to be square. Keep that in mind for the things that are following. The following statements are equivalent. That is, for a given A, the statements are either all true or all false. And the first statement is A is an invertible matrix. And that's kind of one of the important ones you could highlight if you want. So if A is invertible, all of these other things are true. If A is not invertible, all of these other things are false. Let's take a look in particular at the new things that we're adding. All right. The following statements are added in, it says section 2.8. I think that should probably say 2.9. That's where we are now. Anyway, look, statement M, the columns of A form a basis for Rn. We saw that happen in the identity matrix, but you could imagine that it could also happen for other matrices. The column space of A is all of Rn. Again, we saw that happen with the example where we did the identity matrix, but maybe it happens for it. Apparently, this says it happens for all invertible matrices. So I guess what happens is if a matrix is invertible, that says that A has n pivot positions. If n has n pivot positions, then the reduced row echelon form looks like it would have a form that looks like the identity matrix. So both of these things would happen. Statement O seems like it follows from statement N, the dimension of column space A. Is that right? N and O go together, I think, very quickly. Oh, wow. Statement P also goes along with statement O and statement N. Those all go together very quickly, if you know the definition of rank. And then this says something about the null space. The null space would just be the set containing the 0 vector. The 0 is in bold to indicate that it's a vector. Yeah, that makes sense, because if the rank is n, then the null space has to have just the 0 vector so that the nullity is 0. So Q and R seem to go together. So we're just adding some things that use the new terminology. Let's zoom out again. Can we prove these? Do you think it's easy to prove these ones? I think it's easy to prove these ones. So let's do a proof of the new statements so that they can get absorbed into this theorem. Proof of new statements. You might even say some of the statements are so similar that it seems like they shouldn't even be separate statements, but that's okay. How about, I want to prove, we need to loop this in with the old statements, right? In order to show that this actually gets tied in, somehow it needs to get connected. But let's start with statement M. The columns of A form a basis of Rn. Looking through statements A through L, do you see one that we could tie this in with? There might be more than one correct answer to this. I think we can connect this to statement H. Statement H says the columns of A span Rn. So I'm going to say that this is true by the definition of basis. All right, so there might be other ones that you could connect it to, but I think connecting it to H is the easiest, and that's if and only if. That's two ways. Next, I'm going to say that we can show G implies N, that if G is true, N is true. And that is because col A is the set of all vectors B for which AX equals B is consistent. What else have we got? So we're tying in, we're trying to tie in as many of the new statements as we can. How about, I said that N and O and P, they seemed like they all went together. And I'm just going to say that those implications follow by the definition of dimension and rank. Okay. I'm going to say statement P implies statement R by the rank nullity theorem. It just seems like we were going to use that at some point, right? I'm going to say statement R implies statement Q by the definition of dimension. We still have one more thing I need to do. One more thing, and then I'll show you how we've added all of these statements. Look at this last chain of arrows we've made. N implies O, implies P, P implies R, R implies Q. So we've gone from N to Q. We need to somehow go from Q. We need to tie that in to like the original theorem. We need to connect that to some part of A through L. So do you see anything from A through L that you think Q implies? Q says the null space of A is just the zero vector. I see one. Again, there might be more than one answer, but I think that there's one answer that's going to be the easiest for us. I think that this implies statement D by the definition of null. Okay. So, what did we just do? I'm going to say end of proof. We proved the new statements that they are equivalent to the old statements. We just did. You know how I drew a diagram when we first talked about the IMT? Well, I'm not going to draw the whole diagram because now we're covering like most of the alphabet. But what we did was we can draw a diagram with some of the, we'll have the new letters. We'll have the new letters. Here's the IMT as we know it. We knew it previously as statements A through L. First, we tied in statement M. We did M if and only if H. So that connects M to the IMT and shows that M is equivalent to all the other pieces of the IMT. All right. Then we started from G, and we showed that G implies N. And then we started on this big chain, didn't we? We said, all right, well, N implies O. I'm going to zoom in on this. N implies O. And then we said O implies P. And then we said P implies R. And then we said R implies Q. And then I said it was important that we needed to somehow tie Q in with the older statements of the IMT. And we showed that Q implies D, which was already part of the IMT. That's a cool little loop that we made. And we closed the loop. So now everything in the original IMT was equivalent to each other. And now we have this loop as well. So, for example, if you have a matrix and you know that one of the original statements of the IMT is true, for example, maybe statement A. Statement A is an invertible matrix. Let's say you have a matrix and you know it's invertible. Well, it being invertible implies everything in the original IMT, plus it now implies M. It now implies G, which implies N, which implies O, which implies, right? And it goes all the way around. Or you could say, on the other hand, suppose you have a matrix and you know that one of these new things is true. Like maybe we have a matrix and we know that the rank of A is N. That's statement P. So let's say I have a matrix and I know statement P is true. It implies R, implies Q, implies D, which implies all of the things from the IMT. So if the rank of a matrix is known to be N, that implies the matrix is invertible, it has N pivot positions, A transpose is invertible, you name it, all that stuff. So I'm going to zoom out now and write some stuff off to the side. So the new statements become a part of the IMT. I think I used the word absorbed. It's like they get absorbed into it. Maybe a better way to describe it is to say the theorem has grown, has expanded to include a lot. Now it has 18 statements. And that's A through R. If one is true, they all are. If one is false, they all are. So it's called the invertible matrix theorem because statement A says the matrix is invertible. So it basically says, you know, if a matrix is invertible, you get these other 17 statements that are also true. If a matrix is not invertible, you get these other 17 statements that are also not true. And at this point, I want to remind you, because I've been saying, you know, you have a matrix A, this and that about a matrix. I want to remind you the IMT is for square matrices only. A is said to be n by n in order to apply all of these things. Now, if you have a matrix that's not square, you know, it's some other rectangular shape, can some of the things in the IMT be true? Sure. Yeah, some of them can. But the theorem is talking about them all being all true or all false. That's for square matrices only. You know, I'm looking through and I'm thinking I could make a rectangular matrix that's not square that has statement E being true. Or I could make one that has statement E being false, you know? So it's a different discussion when matrices are not squares. Plus, a matrix has to be square in order to even potentially be invertible. Let's see, did we have anything else to talk about today? I guess we've got one more thing. I've got a question for you. So we're going to move all of this away, make room for a question. Let's try to apply some of this. So I'm going to ask you to try it, but I'm going to write 3 questions. I'd like you to wait till I write all 3. That's not supposed to be is. That's supposed to be if A is 3 by 3 and the rank of A is 2, is A invertible? Don't answer it yet. Wait till I write all 3. Part B. If A is 3 by 3 and the rank of A is 3, is A invertible? Part C. If A is 3 by 2 and rank of A equals 2, is A invertible? And in all cases, I'd like you to, briefly explain why. Briefly explain why. All right, so I'd like you to pause the video and give this a try. So these are just yes or no questions, but I think we can give a brief explanation of why it's yes or why it's no. For part A, 3 by 3 matrix, the rank of A is 2. I am going to say no. No, A is not invertible. My reason? If P is false in the IMT, then A is false. That's how I know. We have a false statement in the IMT. Therefore, all of the statements in the IMT are false for that matrix. Okay, that's cool. The rank wasn't big enough. The rank was too small. That's one way to think of it. Oh, I guess that kind of leads us into part B then. Matrix is 3 by 3 and the rank is 3. Is A invertible? Yes. Because if statement P is true, then statement A is true. So you see how we just answered questions about whether or not a matrix is invertible, where I didn't give you the matrices. We don't know what numbers are in the matrices. I don't know what the matrix looks like. I guess I know the size and the rank, and that's all we need to know to answer this type of question. That's pretty cool. We didn't have to do any row reduction. We didn't have to find a determinant. We didn't have to do that big process for finding the inverse of a 3 by 3 matrix. We didn't have to do any of that. This is a really nice shortcut if you just want a yes or a no. Now, for part B, you know, the IMT tells us, yes, the matrix is invertible, but it doesn't actually tell us what the inverse is. In order to find the inverse, you would have to do more work. All right, part B. If A is 3 by 2 and the rank of A is 2, is A invertible? No. My reasoning for that is only square matrices can be invertible. The IMT says nothing about 3 by 2 cases. I'll put that second sentence in parentheses. The first sentence I wrote is the real reason. No, it's not invertible because it's not square. So some square matrices are invertible, some square matrices are not invertible, but a non-square matrix is never invertible. Doesn't matter what the rank is. I mean, it could still have a rank. It can still have a rank and a nullity. It can still be a matrix we're interested in for other reasons, but it can't be invertible. And by the way, the rank nullity theorem still applies to the 3 by 2 matrix. So there's still other things we can do with those matrices. All right, so that's the end of it. That was the last example that I had for this lesson. So these last two lessons that we did, they kind of go together, right? Because we talked about subspaces, we talked about basis, we talked about dimension and rank and nullity, and it all goes together. So make sure that you study these two sections together. And I'll tell you where we're headed next in the course is we're going to revisit determinants. Now, you know that I've been talking a lot about whether or not a matrix is invertible, and it seems like that is somehow important for linear algebra. And at least in the 2 by 2 cases, whether or not a matrix is invertible seemed like it had to do with the determinant. But we didn't really talk about how to find a determinant of a larger case. So that's coming soon. All right, so some of the big ideas in the course at this point are invertible matrices, the invertible matrix theorem, subspaces, basis. A basis is an important idea. Understanding what span means, and I guess dimension. So maybe those are 6 important things at this point. And the rank nullity theorem. Let's add that. Let's say that's also another big important thing. Okay, so we'll wrap it up here, and I'll see you next time for a lesson on more about determinants. Take care.